So like I said, if you've got a multiple degree of freedom system that's undamped and it's forced, then you've got this equation, okay? And what we do is we apply a substitution. And that substitution is this, okay? So x is phi, which is known as the modal matrix, okay, times by q, which is a vector of modal variables. This is a matrix multiplied by q, which is our vector of modal variables. Okay, so that's phi. Greek letter phi is the modal matrix, and q is our modal variable. And if we substitute that into our equation of motion, obviously we replace x double dot with phi q double dot, replace x with phi q, and obviously there's no x on this side, so we just leave that as it is. Okay. Now we apply a trick to this. What we do is we pre-multiply each of those terms by the transpose of phi. Okay. Okay, so we pre-multiply each of those terms by the transpose of phi. Okay, and that term goes out in the front. And assuming your phi term is correct, it just so happens that basically this term, okay, this term becomes 1, or the identity matrix. You've got a diagonal matrix with 1s down the middle, okay? All the other terms are 0, and that's known as the identity matrix, I, okay? And if you've got phi correct, then this term becomes a diagonal matrix, okay? All the off diagonals are 0, down the middle you have omega I squared terms. So if you've got a 2 by 2, because you're dealing with 2 degrees of freedom, this would be omega 1 squared, and this would be omega 2 squared. All the other terms are 0. Okay, if phi is correct, then this term becomes 1, this term becomes omega squared. Notice that we've pre-multiplied the force also by the transpose of phi, so we have to deal with that term separately. So we deal with that. We just rename that P of t, because if we've got a matrix here times by a vector, you're going to end up with another vector. Okay, if this has got 3 terms in and this is a 3 by 3, you end up with a 3-term vector here. And basically, where I've called it P, you can call it anything else, but basically they are known as the modal forces. Okay, they're not real forces; they're modal forces because we're dealing with modes, hence the name. And so obviously what we can do is we can replace that therefore in the equation of motion, and you get this as your equation of motion. Identity matrix times by your q double dot vector plus the omega squared, okay, terms in the diagonal, times by your q vector equals your modal forces. Now if we were to write that out for 2 degrees of freedom, we can say that we end up with equations that look like this. This is for I degrees of freedom. Okay, and so obviously for 2 degrees of freedom you end up with this. Okay, so you've got q1 double dot plus omega 1 squared q1 equals p1t, and you've got q2 double dot plus omega 2 squared times q2 equals p2t. For undamped systems, they will always have this form. Okay, we'll talk about damping later, but they will always have this form. And those equations are uncoupled together. The motion of, well, the q1 does not depend upon q2. There's no q2 term in this equation. And likewise, q2 does not depend upon q1. There's no q1 term in this equation. So these are very simple and straightforward to solve. You can solve that one individually from that one and vice versa.